Okay, we're back with some couple of small loose ends from the previous unit, or should I say from the previous week's stuff. We were learning all about occupancy problems, which is really, even though it's in chapter 8, is kind of an extension of the combinatorics that we had been doing. And in some communication with some students, there were just a couple things which I realized could be done a lot better. So for starters, consider one of the 8 occupancy problems. The occupancy problem in which objects were indistinguishable, containers distinguishable, and no container can be empty. So this is one of the 8 problems, and I explained it in a way which I think I just got from Gossett. I think I did it the way he does it, and it was not wrong, but it was maybe confusing and convoluted, and a student brought it up to me in a Zoom call that there is a better way of thinking about it. Okay, so just very quickly, imagine that this is the situation. We have 11 candies, and 4 kids come to the door with their Halloween trick-or-treat baskets, and our goal is to distribute the 11 indistinguishable candies, object indistinguishable, to the 4 containers which are distinguishable. And we want to give at least 1 candy to every kid, so no bag can be empty. Well, the way I said to do this in the video of the lesson, and also when going over the homework problem that was like this, I said the following. I said, well, look, if every kid has to get, if no bag can be empty, every kid has to get at least 1 candy. So distribute a candy to each kid. Okay. Well, if we distribute a candy to each kid, then now we've satisfied the fact that no container can be empty. So now 7 candies remain. And if 7 candies remain, now I have ultimately a objects indistinguishable, containers distinguishable, empty problem on my hands, because now I can distribute the 7 candies in any way I choose, including where no kid gets one. And so now this becomes a stars and bars problem. So this is actually something that we knew how to do before we learned about partition numbers or Stirling numbers of the second kind. I may have said that already. Anyway, how do we do it? Classic stars and bars. We think of the 4 kids as being divided up into 4 sections with 3 vertical bars, and then we place our candies however we want. And so one option for the candies is like this, in which as no stars were placed between these 2 bars, it means that this kid 1, kid 2, kid 3 gets no candies on round 2. But he or she already got the candy from the first round. Okay, and so then the answer is I have 7 candies, 3 bars, so the answer is 10, choose 3. And that is correct. But there's perhaps a better or another way of thinking about it that's more straightforward. This is sort of a one-step process, which is now what I want to rule out are these situations in which 2 bars are adjacent to each other. That's sort of an invalid situation because it means that the kid between those 2 bars got no candies. So instead, this is an alternate solution, take the 11 stars, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, lay them out, and now let's simply place the bars in and amongst the stars in such a way that every kid gets a candy. Well, if every kid gets a candy, then I can't put a bar over here to the left of the leftmost star, because that would mean that the first kid got no candies, and I can't place a bar to the right of the rightmost star, because that would mean that the final kid 4, received no candies. And so I really only have the following spots to place the bars. That's 10 spots. And so there are 10 different spots where I can drop bars, and if I drop a bar, for example, here, 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 and here, then that's just a valid way of dividing up the candies into, there should be 3 total bars. That's a valid way of dividing up these 11 candies into 4 sections for each of the 4 kids. And in this case, kid 1 gets 3, kid 2 gets 2. But because I'm only allowed to place the bars in the spots in between stars, there's always going to be a star between every 2 bars, at least, and so that solves the problem. And so the answer is, of the 10 spots between stars, choose any 3 of those spots for your 3 bars. And so it's sort of 10 choose 3 kind of directly, so to speak. Okay, that was loose end number 1. Loose end number 2 is, okay, I hesitate to return to this. If you've been watching every single video since school closed, then you will have watched the video where I totally lost it and just kind of stared blankly for 3 whole minutes. And that was this, this combinatorial proof that PNK is the sum from I equals 1 to k of Pn minus Ki. And while I did eventually, well, I solved the problem in advance, I could not find my thoughts during the taping of the video. I recovered and did remember. Then I just didn't bother actually explaining it very clearly what was going on. So it's possible you watched the entire thing and we're still lost. So okay, in like 2 minutes, let me do this again. Well, what is PNK? This represents so sort of my claim is both sides count the number of ways to divide n objects, indistinguishable objects, into k piles. And the left side is the very definition of PNK, and then it's the right side which needs to be argued. And so what we're going to do is perform sort of casework. I hesitate to use the word partition, but divide all partitions. Divide all partitions of objects into containers by the number of piles with greater than or equal to 2 objects in it. With greater than or equal to 2 objects in it. In other words, when I did this, originally I did this with puppies, and puppies didn't like to be alone in a pile. They'd like to have, they were happy when there were 2 puppies in a pile or more. Okay, and so here I'll just call them objects. Okay, so let's just suppose, and now I'm just going to do the combinatorial proof. Suppose that a partition, so this is one of the things that we're counting on both sides. Suppose a partition has exactly I piles with greater than or equal to 2 objects in it. And now here's the picture. The picture goes like this. I have, and this is the picture I should have drawn. So you have your various piles, right? So pile, 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 dot, 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 pile, pile, dot, dot, dot. Okay. And let's suppose that there are k, and then I'll just talk out the rest, because I've run out of board space anyway. So I have k total piles, and my overall thing happening on the left is to divide that. Oops. Oh man. My plan on the left is to divide the n objects up into these piles, such that no pile is empty. But now I'm further looking at only a subset of those, the ones in which every pile has greater than or equal to 2 objects in it. And I'm supposing that I of these piles have greater than or equal to 2 objects in them. So let this be I. Let this be over here in this kind of blue. Let this be the I piles. And so I'm looking at a partition in which there are k total piles, but I of the piles have more than 2 objects in them, which means that k, and so the rest of these piles have just 1 object in them. Well then, okay, I think the answer to this is clear, because if every one of the k piles has to have an object in it, then the first thing to do is to just put an object in every pile. Having put an object in every single pile, then there are n minus k objects remaining to disperse to the piles. But precisely I of the piles have greater than or equal to 2 objects, and thus the rest of these piles over here are only going to have that one object. And so how the problem now reduces to how many ways to distribute n minus k objects to I piles, and that's exactly what Pn minus ki is. And so it's actually quite clear and simple that there are this many ways, Pn minus ki, to distribute n minus k objects to I piles such that no pile is empty, and that counts all the partitions in which exactly I piles have greater than or equal to 2 objects. And since that holds for every single I, then and since every partition is going to have some number of piles with greater than or equal to 2 objects, possibly none, in which case what happened? I has to be at least, I don't think I does have to be 1. I think I could be 0. Yeah, that's kind of interesting. But if exactly especially iPods have greater than 2. Yeah, the only way. Well, okay, I'll just stop there. I think this is good. This is a good explanation. I think I was about to say something stupid, so I will stop. Good. Last thing. Second to last thing. Yeah, you could have no piles with greater than or equal to 2 objects in it. That would be the case if every single pile had just oh my god. N objects into 0 piles. Yeah, that's interesting. If every object had just 1 pile in it. No, you can't do that. The only way you can do that is if n equals k. And if n equals k, then this whole thing is just like, okay, I'll stop with that. There might be some edge cases that I'm not explaining perfectly, but that's good enough. Okay, what else were we going to do? The thing that you might actually consider to be a loose end is this number 25, and I had done this number 25 in the past, but I was not totally confident that I was ready to present this in a way that was good. I was stumbling over my words a little bit when I tried to rehearse this problem to myself. This was the last problem from the homework. And as of the time of taping, 15 of you still haven't submitted this homework, so possibly you'll find this helpful. This number 25 is an exploration of the fact that, well, okay, I'll start. It introduces this new combinatorial construct, TNK, and this is the number of ways to partition a set of n elements into exactly k non-empty ordered subsets. Okay, so this is in fact just sort of by definition the solution to the objects distinguishable by saying a set of n elements. We assume there are n different elements. Containers distinguishable, and no container can be empty. And so how did we solve this problem originally? Well, okay, so the first thing that part A says is to establish that T and K is just K factorial times S and K. And of course that's totally true, because S and K is the number of ways of dividing n distinguishable objects up into K indistinguishable piles where no pile can be empty. And we introduced this as kind of a primitive, although there was a recursive rule for calculating these. And of course, if the piles are all indistinguishable from each other, then if you want to pass those piles out, so to speak, or label them or order them into subsets, not subjects, subsets. Into exactly the ordered subsets. Yeah, so if you now want to disperse, so to speak, these piles to individuals, or to label the piles, or however you want to put it, then there are k factorial ways, since there are k piles, there are k factorial ways to order them. So this, I think, relationship is clear, and that's actually how we solve the objects distinguishable containers distinguishable, not empty problem. This was in the lesson, this was we're the kindergarten teacher now, passing out the candy bars, by simply taking this as a primitive and multiplying by k factorial. Okay, well, this rest of this problem, in fact, comes up with a formula for T and K. And that's kind of the big goal. And this formula is actually in terms of simpler, this formula is in terms of simpler things like just factorials, sums and products of factorials. So it was a little bit of a lie when I said there's no closed form expression for the Stirling numbers of the second kind. There in fact is. But it's sort of maybe advanced or something. Okay, so let's do this. I'm just gonna talk out a proof of T and K. What is T and K? I'm not gonna write this down because I think I'll just say it out loud. Or maybe I write a little bit down. Okay, so I'm gonna do a combinatorial proof, and the proof goes like this. Suppose there are n students. And there are k elementary schools. And the problem is, how many ways are there to distribute the n students to the k elementary schools where no elementary schools are empty? That's basically the heart of this. So, of course, each child can go to any school. The children are all distinguishable from each other. The containers are distinguishable as well because the elementary schools are all different. They have different names, they're different addresses and different teachers and things like that. And we don't want there to be no students at a school because that would be silly. So how many ways are there to do this? This is the meaning of T and K. And we're going to figure this out right now. Okay, well, first you might think, first thought is that, is it just, can I just, for every kid, just send them to whichever school I want? If we do that, then going through students by student, the first student can go to any one of the k elementary schools. The second student can go to any one of the k elementary schools. So it's k times k times k times k n times. And so the answer is k to the n. Okay, but that is not the answer to our problem because our problem insists that the elementary schools be non-empty. Whereas in this method of disbursement of students to schools, we end up with some schools with no students in them because we were free for each kid to decide where to send them, so maybe some school is empty. And so what we need to do is we need to subtract out, and here I am copying off of a student who already submitted their homework using their notation and language. He created a new construct, ENK, and he said, okay, let this be so let this be the number of, I think E stands for empty, the number of assignments in which, trying to plan my white space here, it's not really working, number of assignments in which at least one school is empty. School is empty. And so, if this counts every possible assignment of students to schools, and we subtract out all the schools in which at least one of the schools is empty, if we subtract out the number of ways of making these assignments of students to schools in which there is an empty school, a school with no students in it, then that will give us the answer to the problem that we want. So that will be this will be TNK. Okay, so the question now boils down to what is this ENK? So how do I find the number of schools for which this is true? Okay, well actually I'll sort of start my work down here maybe. So let A1, this might be clear to some people, this might not. Let A1 be the set of assignments in which school 1 is empty. School 1 is empty. So of all the possible ways of assigning students to schools, let this be the set of all the assignments in which no student is assigned to that school. And then let A2 be, again, blah, 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 in which school 2 is empty. So I'll just do that, right? Let A2 be all the assignments in which school 2 is empty, etc., all the way down to, because there are K schools, this is the one in which school K is empty. And so what is ENK really? ENK is the number of assignments in which at least one school is empty. And so what we want are all the assignments in which school 1 is empty, and take all the assignments in which school 2 is empty, and all the assignments in which school 3 is empty, all the way up to all the assignments in which school K is empty. But note that there might be considerable overlap between these sets, but this precisely, this set, which is the union of all of these, is what I'm looking for, right? It's all the assignments of students to schools in which at least one school is empty. And I need to find out how many of these there are. That's what ENK is. Okay, well this suggests that we should use the inclusion-exclusion principle. And if we use the inclusion-exclusion principle, we get, by the definition of inclusion-exclusion, or by that theorem, then we get that this is the sum of all the sizes of all the singleton sets minus the sum of all the sizes of all the pairs of intersections. So that's AI intersect AJ. I'm trying to squeeze this in. And I'll just write IJ, a light notation kind of step here, plus the sum of all the and then this is AI intersect AJ intersect AK for IJ and K. And then like etc. Okay? And so this is just more or less a straight way of stating what the inclusion-exclusion principle says. Okay, so here's where I found it very difficult to say in words what this first term represented until I practiced sort of over and over again with myself. What is this? What is AI? AI is the number, or rather the size, the absolute value of AI, or the magnitude of AI, is the number of assignments in which school I is empty. Okay, and what's the answer there? What is the size of AI? It's going to be, if I know that school I is empty, then I have basically n students to distribute to k minus 1 schools. And so, therefore, I have k minus 1 choices, because one fewer school, because school I is empty, for student 1. And I have k minus 1 choices for student 2. And for each student, I have k minus 1 choices for where to send them. And so this is k minus 1 to the n. But now, and I hope I'm being clear, if I take the sum of all the a sub i's, this just counted how many assignments in which a generic school is empty. But if I'm adding all these up, as the inclusion-exclusion principle says I should, then this is going to be k times that. So I get k times k minus 1 to the n. Man, I really need like a big board. This is very depressing. Okay, now looking here inside this AI intersect AJ, this is the number of assignments in which schools I and J are empty. That is the meaning of AI intersect AJ. AI is the set of assignments in which school I is empty. AJ is the set of assignments in which school J is empty. So the intersection of AI and AJ is the set of assignments in which school I and school J is empty. What is, I have to write very small, what is the size of AI intersect AJ? So now I'm taking sort of two generic schools, I and J, and asking how many assignments are there in which those two schools are empty. Well, if those two schools are empty, then I have two fewer schools to send my N students to. And so I have only K minus 2 choices for student 1, K minus 2 choices for student 2, etc., all the way up to the N. So there are K minus 2 to the N ways to do that. But now, when I perform the summation, what do I get? I'm summing all of these up. Well, what I'm now doing, and that's what the inclusion-exclusion principle does, is it sums among every pair of students. And so, how many sort of pairs of intersections are there? Well, the answer is that there are K choose 2. So that's where you get K choose 2, K minus 2 to the N. This is so frustrating. Okay, and so, I just gonna give myself more room somehow here. By erasing important things. Let's just do one more. What is this? This is the number of assignments in which schools I, J, and K are empty. And so I need to find the size of AI intersect AJ intersect AK. And now I think you're getting the hang of this maybe. Now I have 3 fewer schools to assign students to. So I have K minus 3 choices for who to send to school 1, K minus 3 choices for who to send to school 2, etc. So all of that is going to the N. And then when I add them all up, this is I, J, K. So I'm taking now the sum of all of these AI intersect AJ intersect AKs. Then what do I get? Well, I get, now I have to sort of count each one of these for each one of these triples, there are K minus 3 to the N ways of assigning the students when those 3 particular schools are empty. But there are K choose 3 ways of grabbing a sort of triple of schools. Okay, and so after all the sort of dust clears, what I end up with is that ENK is the sum from I equals 1 to K, it's just a straight inclusion-exclusion, of -1 to the I plus 1, so this flips every time, positive, negative, K choose I, K minus I to the N. This is just this formula emerging over here, but you sort of, you just follow it. And having figured out what that is, then we go back to TNK. What's TNK? It's K to the N minus this, so minus the sum I equals 1 to the K, -1 to the I plus 1. Yeah. Well, okay. It's just minus this, right? So it's minus this whole thing, as we previously said. I erased this, and so now when I distribute the negative through the summation, every sign just flips, and so that's how I end up with this final formula that TNK is k to the n plus the sum from I equals 1 to k of -1 to the, this becomes I now, k choose I, k minus I to the n. And finally, if you are a very fancy person, you can observe that, this is how I think about it at least, that k to the n is just k choose 0 times, which is k, k choose, k choose 0, which is just 1, times if I is 0, then it's just k to the n. In other words, when if you set I equals to 0, I equal to 0 in this formula, you get this. And so you can write this more succinctly, but possibly more obscurely, as I equals 0 to the k, -1 to the I, k choose I, k minus I to the n. And when I is 0, you just get that first term. And so if this is the formula for t and k, then to get the formula for s and k, which perhaps was our goal, then it's just going to be that divided by k factorial. Did I do that right? Yeah. Of course I did. Yep. So it's going to be that divided by k factorial. Okay, so this gives an actual way to compute sort of directly, so to speak, Stirling numbers of the second kind. Oh boy, this is taking forever. Let's just do one more thing, which is an example of Stirling numbers of the second kind. One more example of using this, which shows this in action. And actually, if you sort of Google Stirling numbers of the second kind, this is how they'll often teach it. Although for Gossett, this is just kind of an obscure exercise. So I often gave this problem on a packet for functions. So it's possible if you took functions, you saw this problem before. It's very hard. It says, okay, it's an example of learning and applying these things called injections, surjections, and bijections. And what are these things? This is kind of a discrete math topic. It's something we talk about in logic a lot. Injections are functions which are one-to-one. So these are functions in which here there's a domain, here there's a codomain. So this is like some set A, and this is like some set B. And a function is an injection if for every element of the domain there is, or rather I should say, what makes it a function is that every element of the domain is matched to just one element in the codomain. But if it's an injection, then